Good evening, class. Today we're going to talk about Chapter 5. This was the chapter about pneumatics and hydraulics. Okay, now I assigned it last week, and what I want to do tonight is we'll go through the chapter, and then we'll go to the answers, question and answers, which were pretty easy. First thing, what are hydraulics? And pneumatics. Okay, the pneumatics we'll start with first. Pneumatics is the study of gases, usually air, and it says here it's common usage in plumbing. Now, the definition for this one was towards the end of the chapter, and we run into that quite a bit out in the trade. Example of it would be the expansion tank on a X-Trol tank, the X-Trol tank on a boiler. That small tank that's about a couple of gallons has a diaphragm in it. We've talked about it before, and it allows for the expansion and contraction of the water, which, remember, the water swings about 20 degrees from 180 to 200. So it's always expanding and contracting. Water itself cannot expand and contract much at all. And if your air tank is waterlogged, if your X-Trol tank is waterlogged, of course, it'll trip out the relief valve. And if it trips the relief valve, some of you guys probably already know this, if it's a valve that, unless it's brand new and you're testing it, once it's been installed for a while, once it trips, you're not going to be able to save it. You're going to have to replace it. Okay, so that's pneumatics. It's a study of gases, compressible gases, what they define it as, and it says usually air. Okay, and hydraulics is a study of fluids, all right? And typically for us, it's water. Okay, so let's get started with this chapter. So this will be on page 103. Well, actually, I know you've only got several pages, just enough for the chapter itself. So let's take a look at that. The first page, page 1, what is 103? And they're talking about a cubic foot of water. Now, remember, this is not the mass code. It's pretty close. It's not bad, but it's not quite our code. Now, they use an example of 62.4 pounds for a cubic foot of water. We use 62.5. I believe the real answer is somewhere in the middle. It's about 62.45. Okay, it's going to change our answers just a bit. But you'll see that when we get to the question and answer portion of the book, the difference in the way that we might do it and the way they do it is almost nothing. There's almost no difference at all. Okay, so they're talking about, they get right into the weight of water and a cubic foot of water, 1 cubic foot on top of another. My advice is stay with pounds per square inch. Okay, pounds per square inch, right? Don't get into pounds per square foot, all right? It gets very tricky. Remember, a square foot would just mean you take the square inch, multiply it by 144, 12 times 12, and that's a square foot. So if you got 1 pound pressure per square inch, right? And you've got now you have a square of the 1 inch pressing down. Now you're going to have 144 pounds of pressure. Okay? But stay with pounds per square inch. They wander off onto the square foot. Don't worry about it. Now, one thing I want you to take note of, though, and I don't think I talked about this, if they give you a portion of a foot, you got to take that into account. Now, let's write this down before I get too deep here. 1 pound equals 2.31 foot, what they call a head. Okay, so if you had a piece of pipe like this long, 2.3 feet long, which is like 2 1/3 feet, 2 feet 4 inches roughly, it would be 1 pound per square inch at the bottom. Okay? Now, the flip side of that would be how much pressure in 1 foot. right, of anything, pounds per square inch at the bottom. So you got a gauge stuck in, and you have a leg of water a foot high. Okay, a foot only produces 0.434 psi. Okay, these two little formulas here will give you the answer for most of what you need from this chapter in our code. Okay, they get in pretty deep. It's a good exercise. I did it myself. I'm working on it. I did this several years ago, and just to refresh myself, I did it without looking at the answers, and it comes down to the same thing. You need to know this. You're going to lose a lot of questions, or a number of questions, if you don't know these two little formulas. Okay, so please memorize them. They're not going to be part of a chart. Okay, so on page 104, we'll get by page, let's see. There's not much on page 103. They mention the weight of a cubic foot of water. Fine, we've done that before. And then the next page, they have a cubic foot. They show it at the top of the page. Nice sketch. I wish I could draw like that. They have a cubic foot with like an inch of water in it. Now, a cubic foot of water, let's just do one problem like that. So 1 cubic foot equals 62.5 pounds. If they ask you, if this was only, this cubic foot was only 3 inches deep, how much would the water weigh? So what do you got? You got 3 inches over 12, right? Because it's 12 inches high. Cubic foot's 12 by 12 by 12. So that's what? 25%, 1/4. 0.25, right? Or 25%. So 25% of 62 would be now I can do that in my head, but it would be kind of rough. And I don't have my calculator. That's the problem. Okay, let's do the math. Looks like 15.5, which is about right. Yeah, it is right. It's a quarter of 60 is 15. All right. So if you have the water 3 inches deep, here you go. Okay. I don't know if you'd see a problem like that on the math test. You might, but just be ready for it. Again, if you know how to do these two, you can figure this part out. Okay. All right, let's see what else they got in this chapter. Okay, on page 104, they got pressure head. We don't usually, it's not something we usually talk about in our trade, but occasionally it comes up. Now, for example, I'll give you an example of a head of water where we might deal with it. This happened to me. I had to learn this years ago. I was using a 007. Those of you who do hot water heat, I'm sure you're familiar with it. Now, the 007, the green, that Taco green circulator has been around definitely since the 70s, because that's when I kind of came on the scene and went into business in 1970s. And we had that circulator exactly the way it looks today. And it was a good circulator. And I didn't know this, but I was using it to pump water up to a different level, not just to go around in a system, around in circles. It was to actually raise the level of water. And I found out the head of water that pump can pump is like 6 or 7 feet. It wasn't much. But if it's just pushing water through a system, some of you have probably seen a single 007 doing maybe 4 apartments, right, with 4 zone valves. It might even have one 3 stories high. Okay, that's different than a head of water because it just pushes it around in circles. Now, that's for heat. And that's about the only time I remember dealing with like a head of water. Now, another example that they're talking about on page 104 is the base of a stack. All right, so let's say that they're talking about feet. All right. And they mentioned 100 feet. So if you've got 100-foot high, let's say you're working on one of the old folks high-rise towers in the city. There's what, maybe a dozen, half a dozen, maybe 10 of them around, and they're all 10 stories, maybe 15 stories high. They're pretty high. And for some reason you want to figure out, wonder what the pressure is at the bottom of this place. We'll say it was 10 stories. What would be the pressure at the bottom? Well, let's check. Every foot is 0.434. So we go up a foot, 434. We go up 2 feet, 868, 0.868, and so on. 10 feet would be, just move the decimal of a 10-foot head of water, right? Like you do when you underground test for your cast iron or your PVC, if it's residential. It puts a pressure of 4.34 pounds on the system. Okay? So 4.34 pounds per square inch. Now, if you use air or another kind of gas, they require 5 pounds. You guys that use air know that very well. I never did much with the air. I've used it, but I found the leaks are harder to find. I've always used water. So water is actually a little bit less, 4.34 pounds per square inch that it puts on the whole system above that 10-foot piece of pipe. Okay, so if it's 100 feet high, that's easy. You take 100 times 434. I mean, the math is really ridiculous. It just moves the decimal 2 places. So you got 43.4 psi. Okay? Now, just as a matter of reference for you new guys, relatively new guys, 43 pounds per square inch is pretty good pressure. Not bad. Nothing to write letters about, but not bad. Now, the high end is 80. 80 is a little too much. That's where the faucets start banging. Things start banging around. You're getting water hammer issues. You start wearing out your ball cocks and washers and other things above that level. It's also illegal. Okay, so the highest legal pressure that you can have in a house is 80 psi. Anything over that, we gotta work on that. Now, what if you're doing a well pump? Okay, now we did well pumps one night, a month or two, a couple months ago, and remember, I would say 40 to 60 psi. This would be for a well pump. That's the setting on that square D switch. You guys have done well pumps. I suspect that we're going to be talking roughly the same pressure here. Your bosses are probably in that ballpark, within 5 pounds one way or the other. I found this to be good. Don't go too much higher because that little pressure relief valve, I believe it trips out around 75. And I remember seeing one drip once that I was putting in. I don't know if it was set too low. Some of them actually have a setting where I think it was a screwdriver slot, or maybe you just turn it with your fingers, and you can actually change the setting by compressing the spring on the relief valve on a well pump. Okay, which I don't think we talked about before. But the reason I'm mentioning this is that that's what this represents. A pretty good pressure. If you have 43.4 pounds in your customer's house, you shouldn't have a problem. Now, what about on the second floor? If this is on the first floor, what would be on the second floor? Now, this wasn't part of the test. I mean, wasn't part of the lesson. I'm just kind of adding to it a bit. All right, I got 43.4 pounds on the first floor. Now, every once in a while, you're going to run into a fussy customer that can be ridiculous. I had one lady. She was a very nice lady. I shouldn't be talking about it, but she was a nice lady. But she was complaining that she couldn't clean the liner inside a water closet. Now, if you ever reached in the back of a toilet tank, we all have, working on the parts back there, it's usually stained. Now, the reason is there's no glaze on it. It's just that the china itself, which is very porous, and the stains in it are just what's in the water coming into the house. It's got nothing to do with the water going down the drain. We know that. But she was complaining that she couldn't clean it. Now, why would you take the tank cover off and go inside the tank and try to clean it? For one thing, even with a small hand, you can't get all the way around. I mean, the parts of the ball cock and the flush valve are usually close to the sides. But anyway, that was one customer. So there's some customers that could be pretty fussy. So what I'm getting at is you could have a customer that says, hey, I got more pressure on the second floor than I do down in the basement. Well, let's see what that's all about. So let's say we have 45 pounds in the basement. Okay, now I'm going to make the floors 10 feet apart. They're usually less than that. I think we all know that usually a ceiling is about 8 feet. You get a very fancy house, you might have 9, even 10-foot ceilings, but not very common. Or maybe an old house. Okay, but for this house, we're going to make it 10 feet. Okay, so you get 10 feet to the first floor, 10 feet to the second floor. So you get 20 feet. All right, 20 feet. And each foot is 0.434. Remember, PSI. So what is that? It's going to be 868, right? So if I multiply this out, it'd come out to 8.68 PSI. Have to deduct that right here, right? 8.68. All right, I'll just make it 8. So we got 37 PSI. That is a difference, right? If you drop the pressure from 45 down to 37, it would be noticeable. And you might have a customer that would pick up on that. And you could explain to them, the reason for that is this, right? Water has a higher pressure, the lower down you get. That's why the water towers are always, think about the ones in the city of Florida. Over near the Durfee, the high school, there's a huge water tower right at the top of Garden Street and President Avenue, right about there. There's a big tank. Maplewood, another high point of the city. You'll never see a water tower at a low point. It doesn't make any sense. And when you get out into the suburbs, the tanks can be smaller so they can put them up on legs. Somerset, for example. And they put them up on legs, might give it an extra 50 feet, which would give it about an extra 20-some pounds of pressure. Excuse me, just by being up in the air. Now, how do those tanks get filled? I met the guy, and I think I told you, I'm not a tier 1 or 2 earlier this year. I met the guy that used to clean the screens in North Watuppa Pond, which means he's the only person there is that can legally swim in North Watuppa Pond because he puts his scuba gear on. He goes down there and cleans the inlet screens to the pumping station. Right, the water, I've been through there on a tour, and that water comes in, it's all filtered and treated, and then it goes on from there to being stored. So anyway, this is the pressure drop that you would get dropping it 2 stories, or roughly 4 pounds per floor. Okay, at the residential level, you don't usually run into a problem here. Okay, now one problem though, I just thought of it, and this you might have experienced if you live in a 3-decker in Florida, and it's the water piping coming in is through a 5/8 meter, half-inch meter. It's okay when you turn the water on, it runs fine. But if somebody on a lower floor turns the water on, especially hot water, you'll notice, they'll take all the water, right? And if you're taking a shower, depending on what they turn on, you've got either hot or you got cold, right? And somebody might have experienced that. It's very unpleasant. Now, I'm in a modern house. It's probably 28 years old. But the code, when this house was built in Swansea, is the same as the code today, right? It hasn't changed. And it's a pretty good code. You know, you got 1-inch service. It can easily, 1-inch service can provide water for 4 half-inch pipes. Okay, so if somebody's taking a shower downstairs, somebody can take a shower upstairs, not a problem at all. Okay, but in the old days, they'd have just that small service coming in. I guess people didn't, I think they used to take a bath maybe once a week. And so there wasn't the demand for water like there is today. Okay, I just wanted to do a little bit of work with these 2 problems right here. And we're going to move on. I think most of you probably are familiar with pretty much everything I've done because we have gone over it. All right, that was on page 104. Now, 105, there's a very sleek-looking water tower. I don't think there's any around here that look like that. They're usually up on legs. But notice how the height goes up to the top of the water level in that tank. As that water level drops down, right, the pressure is going to come down also. But another thing to notice, Notice how the ground drops away, and I guess that's supposed to represent a home. There's one up on the hill next to the water tank. Now, for those of you who have done a lot of work in the city, you might have noticed the water pressure on the high points in the city, over near Durfee, Maplewood, near the water tank over there, not the best. Now, you go down near the river, down near the Taunton River, and you notice the pressure is pretty good because it's so much lower. All right. And because we're a city that sits from the water level to the area around Diamond, Durfee, it's well over 100 feet high, right? The difference. So the water pressure obviously is going to change. Now, as the pressure, take a look at that water tank on page 105. Now, that's very simple. That 100 foot, which is the problem we just did, that 100 foot would give you 43.33 psi using their formula. Now, also, they use, they don't use, I think it's 4.34. We use 0.434. I think they just use 0.43, so ours is a little more accurate. In any case, at the ground level, notice where it goes underground and drops another 50 feet to that house on the bottom right. And notice that you have to add those two together to get the whole problem. And to the right of that, above the house on the lower level, you see where it says 150, which is the total from top to bottom. And that's what you use to figure out the pounds per square inch. Okay, and so that's 150 feet times 0.434. Let's okay, comes up to 65.1 psi. That's a good pressure. If I had to set a pressure in my own house, I'd like something around 60-ish, 60, 65. Nah, 65 is more than enough. Okay, but that's a good pressure. Going to give you a good shower. You don't have to wait a half an hour to fill up your sink or whatever it is you're doing. Okay, so 100, it takes 15 stories. That's 10 feet per story is the average to get that. But that's the one in the book that you're looking at on page 105, and that's how you find it. Okay. Now, the next one, they're talking about friction loss. And I am not too worried about that. We don't do much with friction loss. If anybody here, I know it's getting kind of late now because we've only got another class left after this, other than makeup. But I'm still looking for the questions for what they're looking for on recent test takers. All right, so anybody who's taken a journeyman or even a master's test, I'd love to get my hands on some questions or even just the general categories that they really emphasized on the test. But I don't remember this stuff about friction. There is some friction involved in some piping more than others. And, they mention at the bottom of page 105, they get into friction loss. Water rubbing against the rough walls of a pipe. Particles of the water striking one another. That's interesting. I didn't know that. Okay, now, here's an experiment I did myself once, many years ago. I'm not sure if it was ice maker tubing or dishwasher tube, 3/8 OD or 1/4 inch OD, which is really small, ice maker tubing. But the best one to take would be do ice maker tubing. All right, take the plastic caps off either end. It usually was a 30-foot roll, if I remember. It's been a long time. Take that, the plastic caps off, right? And now, probably not too sanitary, but you want to just clean the end of it. Blow into the end of it. You're going to think there's something blocking it. All right, because of the small diameter of the pipe, there's a whole lot of friction going through that 30-foot tube to the point where you think that there's something wrong with it. Okay, so there is some friction involved. There is some loss there. And kind of compared to me, if anybody here has worked on a construction site and you got a cheap 16, let's see, number, you should have a number 12 wire extension cord, a good number 12. I've used number 12 house wiring. It's probably not a good idea, but you can put a plug and an outlet on either end. You still got a number 12. That's not a real extension cord. It doesn't roll up, or it's not designed to be rolled up either, but it does work. But anyway, do yourself a favor, invest in a good, like 100-foot number 12 extension cord, right? 14 is not bad. 16, forget it. That's the orange one with all the paper inside and the little skinny wires. Okay, you got 100 feet of that in your right angle drill in your tools. Now, I know you guys are using a lot of battery tools, but if you are using something with a cord and you're running 100 feet, you need something with a heavy wire. Same thing with a water pipe, right? You get some small water pipe, and it's hard for the water to get through, just like the electricity drops off when you use small wire. Okay, let's move on. Okay, now they do have a comparison. It's exactly what I had with the 0.434. Actually, they do 0.43, excuse me. I was using 0.434, which I think is what you're going to find on your, I don't have it in front of me here, but your formula sheet. Okay, check it out. But again, it's going to be close enough. All right, on page 107, this is where they really get carried away with this friction and all that. You can read that. It's very easy to follow, but I wouldn't worry too much about it. Okay, they show water meter, 250 feet. Where are we working with 250 feet of water? We're not. Even a fancy house, maybe 100 feet from the meter to the furthest point, 100, 100 and a quarter. But this here, I don't know. This has got to be a big commercial building. They're looking at 400 feet. So as you read through that problem on page 107, you spend the time on it, you can understand it. Every time you make a turn with an elbow, it represents like 5 feet of pipe, depending on the diameter of the pipe. Now, one thing I forgot to do, and I'm going to have to send it, unfortunately. Again, you're going to be listening to this after I talk to you. If I remember it, there are some pages at the end of this book that are necessary for answers number 7, 8, and also if you do the suggested activities, which I don't usually ask you to do. They call it useful information, and I forgot about that. Like I said, for several years since when I assigned this to you, I hadn't looked at the answers at the time, and when I was doing the answers, I remembered it. Because I forgot to send you those pages. Not a big deal. They're getting into areas that I don't remember this at all on the plumbing code exams in Massachusetts. And if they do ask you this stuff, it's charts. They have to give you the charts. So you just pay attention to the question, follow the chart, the size of the pipe, the length, and you'll get the answer. Okay, so on page 107, let's skip that diagram at the top. Like I said, you can read that yourself, figure it out, and everything you need is right there. Now, water hammer, different story. This is something we do have to pay attention to, and we've talked about it this year. If your boiler is waterlogged, right? If it's the old style expansion tank, and they were actually around before my time because we were using the Well-Xtrol tanks in the mid-70s, just like we have today. And I say Well-Xtrol, the Xtrol tanks, the small gray ones. They've been around a long time. What's that? Going on 50 years. And now before that, we had much bigger tanks. They were probably 2 or 3 times that size. And they used to fit up in the rafters. Some of you guys have probably taken these out when you're changing the heating system. If you happen to have a customer who still has one of those, remember that tank is going to get waterlogged every year or two, whatever, and you have to drain the water out. I don't want to get into that. That in itself will take a while to go through, but you do have to service them every year or two. You could replace them with an Xtrol tank, right? Just take that big tank out and put a female adapter and screw in a modern tank, and you're doing them a favor. Unless you like to go there every year or two and hang around while you're draining water out. Okay, and the water hammer there would be as soon as the hot and the cold, it would like expand so fast it would just trip out the relief valve. It'd be like water hammer. Uh, Now they mentioned water hammer like when you shut a valve off. I'm saying about when you heat the water. Okay, but water hammer normally is if you shut a valve off fast. Now those of you not familiar with water hammer, uh, when you got pressure up to 80 pounds or higher, and you got a ball valve, right? How long does it take to turn the ball valve? Quarter of a second, on, off. And what happens is the water is surging. And they give a pretty good explanation, pretty good diagram here on page 107. Take a look at it. They've got the handle of some kind of ball valve, and you turn it sideways, and it shuts off. Now, a gate valve, now those of you familiar with a gate valve, that's like around old-fashioned water meter. You turn it maybe, 10 not complete revolution, but you know how much your wrist turns at one time. It takes a long time to shut off. That is not water hammer. Even a globe valve, which would be a stop and waste, 1, 2, 3, and it's probably closed. That's not going to be water hammer either because you're closing it slow. But a ball valve is a different story. Fast acting valve, I think they refer to it as in our code book. But when you shut it off suddenly, it can cause problems. Now, they mentioned the pipes coming apart. I've never seen that. I guess it could if it was only soldered just like on the outside, just like tacked on there, like a homeowner might have done it. Maybe that would blow it off, but I haven't seen it. I have seen the pipes jumping around like in the basement when somebody shut the water off, but it bangs. I mean, it really makes a banging noise in the house. Not good. So you got two problems there. You're going to have to deal with the water hammer issue, and you're going to have probably better check the water pressure. Now, how do you check the water pressure in a house? Very easy. You get a gauge that has a hose connection on it, and you go outside or in the laundry sink, even better, because you can do that any time of the year, and you screw it on, then you open up the water, and it goes up to the pressure in the system. Very simple. Turn the water off, undo the valve. Yeah, it might spray out just a little bit, but it'll tell you the right pressure. And in that case, you put a pressure reducer on. Again, most of you, I think, are familiar with it. Over near the meter, put a pressure reducer to take it 80 plus down to 55. It'd be a good setting. You can set the pressure reducer, excuse me. Now, if you don't want to put a pressure reducer on, you can put an X-Trol. It looks like about the size of it's actually about the size of a baseball, and you screw that on near the appliance that's causing the problem. If you have an appliance that's causing the banging, there's ways around it. Okay. Okay, let's leave that alone. We've talked about water hammer before. And the other solution, I remember doing this right like a shower stall to prevent water hammer. You have like elbows going into the valve. Instead of elbows, you put T's, and then you have legs. I think it says 10 times the diameter of the pipe. That's still only 10 inches for half-inch pipe. We used to make them about maybe 18 inches long, 16, 18 inches long. And what it would do is the water would absorb the air over a period of time, and then you'd have to drain all the water out of the system and would recharge it with air, just like the expansion tank on the old boilers. You got to take all the water out, and then you would like put water back in, but it would be pressing the air, the new air in the tank. Okay. Let's see how we're doing here for time. Okay, we're going to have to wrap this up and move on to the other video here. Okay, so what I'm going to do is I'm going to stop right here, and we're going to pick it up.